So the toddler in this video has a mass of 17 kilograms. The bowling ball has a mass of 3 kilograms. The bowling ball exerts a net force of 0.4 newtons as the ball rolls down the bowling lane. Assume that the lane is 18 meters long. Part A asks to calculate the time that it took for the bowling ball to hit a strike. So first we can rely on Newton's first law, which is net force equals m times a. We're given that the net force of the bowling ball is 0.4 and the mass of the bowling ball is 3. Now we want to isolate for A to find the acceleration of the bowling ball. So 0.4 divided by 3 is 0.133 meters per second squared. So that is the acceleration of the bowling ball. Now, we can plug it into our displacement formula to find the time. So delta x equals initial velocity times time plus 1/2 times acceleration times t squared. We know that the ball starts from rest, so vi is 0, we can cross that out. The lane is 18 meters long, so that means that the ball will be traveling 18 meters, so we can plug that into delta x. And we know that the acceleration of the bowling ball is 0.133, and time is unknown. So 0.133 divided by 2 is 0.0665. And we do not know time, so we just leave it as is. And so we divide both sides by 0.0665 to isolate for t squared. We get 270.67. Now, we want to square root both sides to isolate for t, and we get a total time of 16.45 seconds. So that is the amount of time that it took for the bowling ball to hit a strike, 16.45 seconds. So for part B, it says to find the average velocity that the bowling ball travels at. So we can use our average velocity formula, delta x over delta t. We know that the lane is 18 meters long, so therefore delta x will be 18. And given our previous calculations from part A, we know that the total time that it took for the bowling ball to hit a strike, which means that the bowling ball is arriving at 18 meters, is 16.45 seconds. Therefore, 18 divided by 16.45 is 1.09. So that makes the average velocity of the bowling ball 1.09 meters per second. So part C asks to calculate the velocity of the first pin that dropped as the bowling ball strikes it, assuming that the mass of the pin is 1.5 kilograms. So what we could do is we can use the momentum formula, and in this case, the bowling ball hitting the pin is a elastic collision. So therefore, it would be m1v1 plus m2v2 initial equals m1v1 final plus m2v2 final. So now we can start plugging in what we know. We know that, so let's first assume that the bowling ball is mass 1 and the bowling pin is mass 2. So m1 is bowling ball, and then m2 is bowling pin. So the mass of the bowling ball is 3. And then we do not know the the bowling ball starts from rest, so 0. And then the mass of the bowling pin is 1.5, and also the bowling pin starts from rest, so 0. And then again, the mass of the bowling ball is 3, and we do not know the final velocity of the ball as it reaches the first pin. And the mass of the bowling pin is 1.5, and we do not know the final velocity, which is what we're looking for the bowling pin. So, let's first find the velocity of the bowling ball. So what we can do is use Newton's first law, which is net force equals ma. We know that the net force of the bowling ball is 0.4, and the mass of the bowling ball is 3. And we want to isolate for a to find the acceleration, and we get 0.133 meters per second squared for the acceleration of the bowling ball. So now we can plug it into displacement. Oh, no, actually, we can plug it into common form. So we know that the initial velocity of the bowling ball is 0. And we know that the acceleration of the bowling ball is 0.133. And the total distance that the ball travels is 18 meters. So we can calculate this. 2 times 0.133 times 18. We get 4.788 on this side. And we want to square root both sides to isolate for VF. So square root of 4.788 is 2.18 meters per second. So that is the final velocity of the bowling ball as it hits the bowling pin. So now we can plug it in. So 3 times 2.18 plus 1.5 times V2F. We basically know that this side is 0. 3 times 2.18 is 0.54. And this is just like that, 1.5 V2F. And then we can subtract both sides by negative 6.54. We can subtract both sides by 6.54, sorry, not negative. And then 1.5 V2F, and we want to isolate for the final velocity of the bowling pin, so we divide both sides by 1.5, and we get a velocity of negative 4.36 meters per second. So that is the velocity of the first pin that drops as the bowling ball strikes it. Part D asks to calculate the amount of time that it took for the bowling ball to arrive at the 13-meter mark. So what we can do is rely on Newton's first law, which is net force F equals ma. And from previous calculations, we know that the acceleration of the bowling ball is 0.133 meters per second squared. Now that we know the acceleration of the bowling ball, we can just plug it into the displacement formula. We know that the bowling ball starts from rest, so we can cross out that initial velocity. And the delta x would be 13 because it's asking for the time that it took for the bowling ball to arrive at the 13-meter mark. So we know that the acceleration is 0.133. We just plug that in. And we do not know t squared, which is what we're looking for. I'm looking for t, but yeah. So 0.133 divided by 2 is 0.0665. And we can divide both sides by 0.0665 to isolate for t squared. And we get $195.48. We want to square root both sides now to isolate for t. So square root of 195.48 is 13.98. So the total time that it took for the bowling ball to arrive at the 13-meter mark is 13.98 seconds. So part E asks to calculate the kinetic energy that the bowling ball produces by the end of the lane. So the kinetic energy formula is Ke equals 1/2 mv squared. We want to find the velocity of the bowling ball by the end of the lane. So what we can do is use common form, which is Vf squared minus Vi squared equals 2a delta x. Given previous calculations, we know that the acceleration of the bowling ball is 0.133. So we can just plug that in. And the total distance that the bowling ball travels at is 18 meters. We know that the bowling ball starts from rest, so we can just cross that out. And from there, we can just continue our calculations. So This side is 4.78 VF squared, and we want to square root both sides to isolate for VF. So square root of 4.78 is 2.18 meters per second. So that's the velocity of the bowling ball once it hits the end of the lane. So now we want to plug in the velocity into our kinetic energy formula. So 1/2 times the mass of the bowling ball, which is 3, and the velocity of the bowling ball by the end of the lane is 2.18 squared. So, oops, sorry, give me a second. So 3 divided by 2 is 1.5, and then 2.18 squared is 4.75, and then 4.75 times 1.5 is 7.12. So the kinetic energy that is produced by the bowling ball by the end of the lane is 7.12 joules.